In topic 6.6, we're talking about nuclear power, using nuclear reactions to generate electricity. And the way that nuclear power works is it uses the heat energy that's generated by the fission of uranium to boil water, produce steam, spin a turbine, connect it to a generator that generates electricity. So it's similar in some ways to using the fossil fuels to produce electricity, but the source of that heat energy that turns water to steam is different. The source of the energy in nuclear power is uranium. When an atom of uranium-235 is struck by a neutron, it forms a very briefly an unstable nucleus of uranium-236. And this unstable nucleus then splits. That's what fission is, the splitting of this atom. And when it splits, it forms two new elements. Okay, we could see krypton and barium. And it also releases a huge amount of energy as heat, an enormous amount of energy. It also releases 3 more neutrons, which can be used to split another atom of uranium-235. And so we form this chain reaction that releases large amounts of heat energy. So when we talk about a nuclear decay, this term of half-life can be used. And half-life is the time that it is going to take for a radioactive element to decay, for half of the original material to decay. There are radioactive elements that are found in the Earth, and these radioactive elements decay at a given rate, at a relatively stable rate. And so we often use this concept of half-life to figure out how long a material will be radioactive, or to date things sometimes using radioactive dating. So what we see here is just sort of a depiction, that if we have a radioactive element here, okay, and 100% of it is this radioactive isotope. Okay? After a single half-life, only about half of those atoms will remain as the original element. And then after another half-life, there will be just a quarter. And after another half-life, there will be an eighth, and so forth. And so that's what half-life is. And so the fission products that are produced by the breakdown of uranium in nuclear power plants, some of them have half-lives of 30 years. The materials strontium and cesium. Some of the waste products that are produced during nuclear power generation can be tens of thousands of years. And so this is important because this is an important trade-off, a constraint about using nuclear power, and this is one of the reasons why some individuals support nuclear power and others don't. The uranium that's used in most nuclear power plants, uranium can be found naturally in the Earth's crust. Kazakhstan is where most uranium mining takes place. There's some in Namibia, Canada, Australia, you see Uzbekistan and Russia, Niger, China. Those are the main sources of this uranium that's used as a fuel source. And we'll talk a little bit in more detail about how this works, what it looks like, what's going on inside of a nuclear power plant. So the uranium that's used as a fuel source, it's stored in what are called fuel rods. Fuel rods you can see in this model of the nuclear reactor. We can see these orange bars represent fuel rods. Here you see some of the actual fuel rods in a real nuclear power plant. But there are the fuel rods which contain the uranium, and then there are another type of rod that are called control rods. These control rods contain a material that can absorb the neutrons that are produced by the nuclear reaction. And so by raising or lowering these control rods, you can prevent the neutrons that are released from the breakdown of uranium from reaching the next fuel rod. And so you can moderate the pace of the nuclear reaction to generate more electricity, to generate less electricity, etc. Okay, and so this nuclear reactor is what we would call this, is producing huge amounts of heat. Okay? And produces that heat, it heats up sodium or water, and that converts, as it cycles through, it converts water into steam. Okay? And that steam, as it rises, spins the turbine connected to a generator, which generates electricity. Now, obviously, that steam, large amounts of steam are produced, has to be cooled down to cycle this water through the system. And so there's also typically a apparatus for cooling that steam back to water to pump it back to be reused. So this is a separate loop. It takes in cold water, typically from a lake or a natural source of water. That cold water coming in from the outside is used to cool down that steam. Okay, and then that water is typically released back into the environment. This water, as long as everything's working properly, has no radiation, but it is warmer when it's released, and that's another trade-off with nuclear power. So the uranium-235 fuel is radioactive, clearly, and that can have human health consequences, right? Radiation from radioactive elements, if we are exposed, leads to cancer. And so that fuel and other radioactive elements used in this process need to be carefully handled. Okay? And so what we see is the nuclear power plant and its actual operation. We see what's going on here. Okay? After the fuel is used up, it becomes spent fuel, which is highly radioactive. Even though the uranium-235 has decayed, it's still very radioactive. It's still very dangerous. That's that spent fuel. And so that has to be stored in a shielded container to prevent any radiation from leaking out until it can be disposed of. It also needs to cool because it's immensely hot. There's also other materials. These are materials that are waste products, materials that have been exposed to this radiation. Some of those wastes are intermediate level waste. Others are low level waste. But all of these waste products are contaminated and are radioactive. So different amounts, different types of waste have to be handled differently. Some of this transuranic waste, okay, that has a long half-life. These intermediate wastes are stored, okay, until they can be disposed of. Also, the low-level waste do not need to be shielded because they are less radioactive than others. But then the ultimate question is, what do you actually do with these waste products? Where do we put them? Because most of them have long half-lives, they're going to continue to be radioactive. They can be dangerous to humans, to other organisms. They can contaminate the environment. And so there's really not great methods of permanently disposing of this material. Oftentimes they're stored underground in some way. Sometimes these high-level wastes can be stored deep underground to prevent any exposure. The low-level wastes are typically buried as well, but at a lower level. And we'll talk about some examples of what some potential solutions to that might be. And so here's another infographic that sort of talks a little bit about the nuclear waste. Okay, and so I'll just point out a few things here. So if we look at this map here, okay, much of the world has operating nuclear power plants. They are banned in a few countries. We'll talk about where nuclear power is used most extensively. And so the radioactive fission products, the spent fuel, most of that is uranium, okay, and then there's some other products as well. And that radioactive waste has unstable isotopes, which will still continue emitting radiation. And some of these materials have half-lives of 30 years, like I mentioned earlier. Some have half-lives up to tens of thousands of years. Some of these materials can even have half-lives in the millions of years. And so those different types of nuclear waste, low-level, intermediate, and high-level waste, have to be disposed of. Like I said earlier, the low-level waste can be stored in areas near the surface that get covered and encased in concrete, but the high and medium level waste have to be deposited deep underground in geologically stable areas. Okay. This is, there are plans for a way of actually storing some of this nuclear material that have been in the works for a long time. So this is a site that was designated in the U.S. in 1987. This is about 80 miles away from Las Vegas. You can see it here. This is the Nevada test site, is where they tested nuclear weapons during the Manhattan Project. And nearby is Yucca Mountain. Okay, in Yucca Mountain, which we see here, there was a plan to put in a repository where high-level waste, spent nuclear fuel from U.S. nuclear power plants, could be permanently stored. It was approved in 2002, then in 2011, funding was removed. It's very controversial. It's gone back and forth. It is not currently operating. It was on the land of the Western Shoshone people. And so there's various reasons why people did argue against it. It is, and we won't get into all those details here, but it's basically has never functioned. It's not built, and so currently in the U.S., high-level waste have to be stored on site where the nuclear power plants that generate that high-level waste are. They're stored on site, encased in concrete or put in vaults, but there's no overall repository to store all of that material in the U.S. So nuclear power, it's a source of energy that does not release any air pollutants. Okay, so it releases no carbon dioxide, no other air pollutants as well. And when you see sort of a nuclear power plant like this, what you see coming out of it, that's just steam. Okay, that's steam from the cooling water that's being used. So there's no air pollutants that are released, but there is thermal pollution, because there's the heat energy as a nuclear power plant releases the water used for cooling back into a lake, for example. The water is warmer, and that's thermal pollution. Also, the spent fuel and the other lower level waste are hazardous waste that can be dangerous to ecosystems and to human health. This is not considered a renewable source of energy because uranium, the fuel, is not renewable. There's a finite amount of uranium. And there's also the risk of accidents. And so accidents can lead to the release of radiation that can result in serious consequences for the environment. We'll talk about some of those accidents in a minute. So if we're thinking about nuclear power as a source of clean energy, many environmentalists would support the increased use of nuclear power. Others might not. It depends. There's pros and cons, certainly. Nuclear energy is very fuel efficient. A tiny little pellet of uranium fuel contains the same energy as 150 or so gallons of oil. And so that's a huge energy density that releases no air pollution. The cons, however, are dealing with the waste products, potential accidents, and the thermal pollution as well. In New York State, we do use nuclear power. We have a fair amount of our electricity comes from nuclear power. Here are the three nuclear power plants that are present in New York State: Indian Point, 9 Mile Point, J. Fitzpatrick, and R. Regina. And what you'll notice is they are also, there's some near us. Okay? The largest are here, 9 Mile Point. It's up on Lake Ontario. And again, they're built oftentimes right next to, right on the shores of lakes because they can access that water for cooling. Here is where we have nuclear power in the lower 48 states. Okay? Here is sort of the countries and how much nuclear power they use, what you'll notice is there's certainly an outlier, France. France gets almost a majority of its electricity from nuclear power, and that was a decision that was made. And so we can see that France sort of stands out here as a country that utilizes nuclear energy to a very high degree. Throughout the world, from the advent of nuclear energy, there was a rapid increase, but over time, in the last several decades, the amount of new production of nuclear power has leveled off. There's very few new nuclear power plants that are being constructed. It's sort of fallen out of favor. And part of the reason for that is that there have been accidents, and so we can look at some of those. One of the first was 3 Mile Island. This was an accident that happened in 1979. Okay. 3 Mile Island is here in Pennsylvania. And there was an accident that led to the release of some small amounts of radiation. Okay, you could see it's 0.062. But there was no known health effects, no deaths, etc. But this was something that scared people as this accident happened. They evacuated pregnant women, preschool children from an 8-kilometer radius, but there were no deaths involved. Chernobyl was the next major nuclear accident, which you probably have heard of, in 1986 in Ukraine. And this led to 30 deaths from the accident and the evacuation of over 100,000 people. And we can see here, this map shows sort of the spread of nuclear radiation that happened after the Chernobyl accident. And then in 2011, we had the Fukushima accident, okay, which released 770 versus 5,200 for Chernobyl. There were 3 deaths, 80,000 people evacuated in this. This is in Japan. And so these accidents scare people, and they can have serious consequences to human health in the nearby area if there were to be a serious accident. So if we finish up and summarize sort of the non-renewables, this table shows you sort of some advantages of each of these fuel sources, some disadvantages, potential pollutants, general costs, and things like that. So this kind of summarizes oil, coal, natural gas, and nuclear energy. These are the non-renewable sources of energy that we typically use.